Hi, welcome to a new lecture. Today we'll be learning linear regression. We'll try to understand the basic theory behind implementing a linear regression. We will also actually implement it using code in Scratch and also learn how to use packages. So these are all part of machine learning implementation in Julia, and linear regression is probably the simplest and most fundamental ML model. You might actually be surprised that people call it as a machine learning model, but at the end of the day, yes, it is a model which learns on top of the data, and then it tries to make prediction on unseen data, which is what machine learning models do. So as I mentioned, linear regression is trying to create a model that maps from the independent variable to the dependent variable. So if you have a function y equal to f of x, y equal to f of x, x is the independent variable and y is the dependent variable, and there is only one, it's like only one dimension. The independent variables have only one dimension because it's only x and prediction is y, and then the data points for discrete values of x could be something like this. And then you might say that provided that the data is sufficiently linear enough, then you can fit a line through it, and this line is now the model, and these dots are the data points, rather training data points. Now, why is this called as a model? Because we can make predictions using this straight line on data that was not part of the training data. So if these dots were the part of the training data, meaning we knew the xy value pairs for all these dots, then we fit a straight line through it, and then for a new value of x, let's say over here, we can predict that the value of y should be such that it lies on this line, and the value of y will be somewhere here. So this is the prediction. And this is the simplest kind of ML model, where the equation of the line itself represents the model. And it's obviously y equal to mx plus c. But here the learning, what is the learning process here? The learning process is figuring out what should be the m, slope, and what should be the c, intercept. There is one more thing that you should keep in your mind. Often in real life data, you probably won't have just one variable. You will have multiple variables. So if there are multiple variables, even if there are, let's say, two variables, x1 and x2, it's very difficult to plot the corresponding y value. So y could be the third axis coming out of the plane, and then it's very difficult for me to show it, right? But a linear regression in this particular case will create, instead of a line, it will create a plane which fits through the data points. And now that plane will be the model. And for values which were not part of the training data, so training data will be x1 comma x2 input pairs mapped to, let's say, corresponding y. So this is, let's say, x1 comma x2 with index 1 mapped to y1. X1 comma x2, so 1 is the first dimension, 2 is the second dimension, x1 comma x2 index 2 mapped to y2, like that. These are all part of training data. And then the model, which will be a plane in this case, because there are two features or two dimensions for the input variables. That plane itself will be the model, machine learning model. And how does a plane look like in this case? It could be, for example, written as y equal to, let's say, beta naught plus beta 1 x1 plus beta 2 x2. And this is the equation of a plane. All right, so now let's get back to equation for simple linear regression. In fact, a simple linear regression contains an additional term epsilon. So epsilon is the error term, because when you make a linear fit, the line does not perfectly match with the data points. The line is on an average matching with the data points, but not individually at a single point level. So there is always an error, which is the difference between the actual value versus the predicted value. So for this value of x, the actual value is, let me choose a different pen color. The actual value is this, whereas the predicted value is this. And there is a difference between this, and that is the epsilon. So sometimes epsilon can be positive Here, the difference between actual value and predicted value is positive. But sometimes, like this one, epsilon can be negative because actual value is less than the predicted value. So to get the actual value of y from the model, you have to add or subtract an epsilon value. In general, it's just denoted as plus epsilon. So y equal to beta naught plus beta 1 x plus epsilon denotes the exact value of the data point provided you have this model, and beta naught and beta 1 are the learned terms, right? So that is what is discussed here. Dependent variable, independent variable, intercept. So beta naught is the y-intercept. And what is the y-intercept? Y-intercept is nothing but this. Where does the line cut the y-axis? That is y-intercept. In this case, this is the x-intercept where this line cuts the x-axis. In this case, this is the x-intercept. Here, this is the y-intercept, all right, for these two lines. So this is just a definition of the terms. And what about multiple linear regression? Multiple linear regression is simply having multiple features. So I showed you the example of having two features. In that case, it's a multiple linear regression with 2 dimensions. So you have beta naught, then beta 1 x1 plus beta 2 x2. You can generalize this to any number of dimensions. But as the number of dimensions increase, it becomes more and more and more difficult to visualize, because maybe you can visualize a plane, but beyond a plane, how do you visualize a 3-dimensional linear structure? Very difficult. So you can imagine a straight line extended to the next dimension as a plane, extended to a next dimension as some 3D structure, and so on. So in general, mathematically, we can represent it as beta naught plus beta 1 x1 plus beta 2 x2 plus etc. 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 plus the error term. So this could be sigma beta x beta naught plus sigma beta x plus epsilon. This is what is the generalized format of the equation for the actual data point, provided the model. Here the model is all the terms that I have put in this bracket plus added with the error term so that you can exactly match the data point. Often for good models, we just assume that error is considerably small. So we just say that the model itself is making a good prediction on the data points, which is more than enough. Sometimes the error will be so huge for several points, and those are called as the outliers. For example, let's say there was a point, most of the data points, let's say it's here. But sometimes maybe a point can be over here. So this is probably not going to affect the overall model, which is the line. Line may remain at the same place even in the presence of this data point or in the absence. But the problem is this is an outlier because the error here is so huge. So often you have to discard the outliers while defining the model. We will not be going into the details of how exactly you find the outlier and how exactly you algorithmically eliminate them. But just understand that for most of the practical purposes, the error term is negligible. All right, so where are we applying this linear regression? You might be wondering, like, it's such a simple model that how exactly are we going to use a linear model for real life data? So I have provided some examples here, which are real life data sets, which you will find on Kaggle and other platforms. So there is a housing price prediction data set, which is very famous. It's not exactly a linear model, but a toned down version of the same, where the data set only consists of, let's say, the number of bedrooms in an apartment or in a house, and the location, what is it called? The latitude, longitude, address. Based on those 2 parameters, and maybe also based on the size of the house in terms of square footage, you can forecast or you can kind of predict the price of the house. So in the training data, there will be a price. And how is the price arrived? Price is mapped. There is a mapping from size, comma, bedrooms, number of bedrooms, comma, let's say not square footage, location. There is a mapping from these three to the price. And this is a 3-featured data set because size, bedroom, and location are these three are features, which means directly plotting it is very difficult. But if one of these were not there, like for example, if location was not there, then size and bedrooms means the linear regression model is a plane which goes through all the data points in a meaningful way. And for any future data points, meaning for a new house that was not part of the training data set, if we know the size of the house in terms of square footage and if we know the number of bedrooms, we should be able to predict the price as a point lying on the plane, right? So this is a practical application of linear regression for housing price data set. Then there are, of course, estimating sales revenue based on advertisement spending. This is actually quite linear. This I know from experience of playing with Google advertisements. So the revenue you make from the advertisement is in almost all the cases that I have encountered, it's a linear function of the spending. If you spend double, the number of impressions of the Google ads will also double. And then the conversions that you get from the Google ads will be directly proportional to the spending that you make. So there is a linear model. The only question is what kind of what is the slope of the model? Like if you are spending, let's say, $50, are you going to get 50,000 impressions or are you going to get 20,000 impressions? Because there the ratio of impression to spending ratio is different in both cases. So a linear model, regression model, essentially finds that factor. And of course, forecasting index like GDP growth rate or any other thing in the vicinity of, like, if the data set is considered for a relatively shorter amount of time, then you can create a linear mapping from various economic factors, mapping it to indicators like GDP. So there are practically many applications of linear regression, but there are several assumptions underlying the usage of linear regression. I'm not going to list all the assumptions because there are multiple of them, but the main thing is linearity, obviously, because the data set, the relationship between independent variable and dependent variable has to be linear. So how do we know this prior to even making the model? We will know this only, in many cases, we'll know this only after making a prediction where we see that there is a group of data set which is diverging so much from the line from the linear prediction that you are making. Sometimes you can also calculate the R-square value. R-square value will tell you how closely the data points are fitting with the straight line. So for example, when I was working on my research papers, I had a particular data set which was like some sort of non-dimensional charge Q star, or rather it's on y-axis. So some non-dimensional charge as a function of voltage. And I wanted to show that there exists a linear relationship between the charge and voltage. So what I did was I plotted these numbers and for different particles. So one set of data looks something like this. Another set of data looks something like this, right? And if I remember correctly, these were for different particle sizes. If this was not Q star, these were for different particle sizes. And then initially I said that the relationship between these two are like between voltage and charge is like a straight line. But then when I submitted the paper, the reviewers asked me, hey, you have to prove, you cannot just claim that it's a straight line just based on looks. You have to prove it based on, you have to demonstrate it using numbers, and there we use R square. We can also use mean squared error. Mean squared error is something like you take the difference between the prediction and the actual value and you sum it up. So it's basically sum of y predicted minus y actual, y predicted I minus y actual I runs from 1 to n. There are n data points. divide by n and take the square root of this mean squared error. So there are many such metrics which we can use to estimate how good the linearity is in the first place for the data. The second thing is independence. Observations are independent of each other. So what this means is we should be able to independently conduct this experiment to get the data. We should be able to independently conduct this experiment to conduct data. So the fact that we conducted this experiment should not bias the production, like the value that we get from this. So if we call the first one as 1 and second one as 2, now imagine that for whatever reason, if I conducted the experiment 1, the value is this much. But if I conducted experiment 2 after conducting experiment 1, then the value was this much. So this is 1, this is 2. Now imagine another case. I first conducted experiment 2 and then I got a value like this. Then I conducted experiment 1 and then I got a value like this. So here clearly the experiments are not independent, because the fact that you did experiment 1 is affecting the outcome of experiment 2. Or the fact that you did experiment 2 is affecting the outcome of experiment 1. So this cannot be the case, because then also linearity assumption, the linear assumptions behind linear regression is not fully getting satisfied. So observations must be independent of each other. Now, what we want to do is we want to have a look at how do we represent all of this as a matrix multiplication. So why are we suddenly discussing about matrix multiplication? Because we have a lot of data points, right? So for example, in this case, we have X as the data, Y as the prediction. So imagine that we have n number of data points. So then X, if we represent it as a matrix, it will be X1, X2. So here it's not dimension, it's data point, right? So X1, X2, X3, etc. up to Xn. And then the corresponding predictions or corresponding outputs, Y equal to Y1, Y2, etc. up to Yn. So this is the case where we have one dimension. What if we had two dimensions? Then the representation of the Y will remain the same. This is a 1 by n matrix, but the input, this will change to be X11, X12. So the first one indicates it's the first set of data. The second index indicates it's the dimension 1. This is dimension 2. Then this will be X21, X22, X31, X32, like that up to Xn1, Xn2. So the first index indicates that n means it's the nth experiment data point. And this 1 and 2 indicates it's dimension 1 and dimension 2. And in general, if there are n dimensions, or let's say p features, p dimensions, then we can say X equal to X11, etc. up to X1p, because it's the pth feature. And this will be Xn1, and then here it will be Xnp. So this will be like a matrix that look like this. So this is the general representation. And the reason why we represent it as a matrix like this is because then it's easy to implement in code. So now we assume that there are n dimensions for the input features, meaning there are n number of input features itself. And X can be represented as a n by p matrix. In this particular case, we represent it as a p by n matrix, but we can do it the reverse also. We could say that instead of here, each column is a data point. Each column, this the first rounded set of X, they are corresponding to the first experiment, which is the first data point. The last one, this is the nth experiment. All the p dimensions of the input corresponding to the nth experiment. Now, how do we create a different version of this? We could also say that X is mapping to Y, and X is such that every row is an experiment. So the first row, which is X11, X12, etc. up to XP, X1p, is the p dimensions corresponding to the first experiment. Then then x21, x22, etc. up to x2p, then finally xn1 up to xnp. In this case, this is a n by p matrix, and each row is one separate experiment, and this will be mapping to y. And how many data points should be there in y? There should be n number of data points, because there are n number of experiments. Every experiment should map to one outcome. So y should have a dimension of n by 1. So this should be y1, y2, etc. up to yn, right? So this will be the mapping, and this will be n by 1. Previously, it was 1 by n. So these are both telling the same thing, but depending on how you want to do the calculation, you can represent it as n by 1 or 1 by n. But the only thing is then you have to change the dimension of x also accordingly. Anyways, so here we are going with the n by 1 notation for meaning something like this, rather than something like this. So we are not following this notation. We are following this notation. Fine. Now let's see how we can represent all of this as matrix multiplications. So we know that if we had a straight line, we have y equal to beta naught plus beta 1 x, right? So there are actually two terms. One is beta naught and one is beta 1. Now the question is, why have we written something like this? Y predicted equal to x times beta. So remember that these are both matrices. What happened to the constant term? So this is very interesting. So let me just move all of this aside. I just want to explain this to you so that you will understand why we are doing certain things when we write the code from scratch for the implementation of linear regression. All right. So I hope this part is clear why the dimension of the prediction is n by 1. Because there are n number of experiments. Every experiment leads to one outcome. So this is n by 1, right? So the dimension, let's first look at dimension wise. So the predicted y matrix equal to beta x. Imagine this is the case. Then the dimension of this is n by 1. That is clear. What about x? The dimension of x, what should this be? The dimension of x, if you have p features and n samples, we said it's n by p. So what is p here? Features, and n is the number of experiments. So from this, just by looking at the dimensionality matching, we can say that the beta is supposed to be here. We can say that the dimension of the beta should be p by 1. So let us mark that here. So the dimension of this should be p by 1, because n by p dimension matrix multiplied with p by 1 dimension matrix should give us n by 1 dimension matrix. So this is the output, this is the x is the input, and beta is the parameters. Now the question is, how do we incorporate the constant? For that, what we do is, I told you that x equal to, so let's say we have 3 dimensions and 2 experiments. Then all we need to do is something like this. Let's say the input array is something like, if you have n number of experiments, 1, 2, 3, 4, 5, 6. Let's first take the case of having only one dimension, n number of experiments, right? And we said that x equal to n by p, which means I should actually write this as a transpose of this, fine. And y, let's say the prediction y is 10, 20, 30, 40, 50, 60. And the dimension of y should be n by 1, which means if we have only one n number of experiments and one feature per experiment, then it should be like a column. So here also I'm putting transpose, right? Now what we do is we append, so x, instead of it being just 1, 2, 3, 4, 5, 6, we also append an array of 1 here. This is the first thing we do. And x times beta. So for beta, what we need is, we need two parameters, because here now what we are doing is, originally every experiment, like every data point was just one dimensional. We had 6 experiments, and every experiment, the input corresponding to every experiment just had one dimension. But now what we are saying is every input has 2 dimensions. This is the first dimension, the value of first dimension, and this is the value of second dimension for the first experiment. For the second experiment, this is the value of first dimension, this is the value of second dimension. Third experiment, like this, like this. So what we are essentially saying is, for every experiment in the n number of experiments, we have p equal to 2, meaning we have 2 features. So this is n by p, where n equal to 6 and p equal to 2, which means the beta, this guy, should be p by 1. What is that? It should be 2 by 1. So let's say this is p1 and p2. Sorry, it should be 2 by 1, means it should be p1 and p2. So this is 2 by 1. Now, can we expand this to see how it maps with y? And y is this 10, 20, 30, 40, 50, 60, right? Now what we have here is p1 p1 plus 1 times p2 equal to 10. It's mapping to 10. Then p1 plus 2 times p2 equal to 20. P1 plus 3 times p2 equal to 30. P1 plus 4 times p2 equal to 40. So the thing is, we will never get equalities like this. Every single data points will not, if we are assuming that the data points are falling on a straight line, in general, every single data point will not fall on the straight line. We already discussed that. Like you saw that in linear fit, data points will be away from the straight line, slightly above or slightly below. But I'm just showing you the case where it happened to fit exactly on the line. So now you might be able to see the pattern. Now this is of the format beta naught plus beta 1x or beta 1x1 equal to y. And this is of y equal to mx plus c form. So basically what I'm saying is, we can write as matrix multiplication this mx plus y equal to mx plus c form by appending an array of ones as the first column, and then increasing the dimension of the feature, this coefficient matrix beta, by adding one additional dimension. So this originally, this was 1 by 1 because we had only one feature per experiment. But because we appended this array of ones as the first column, then every experiment happened to become a set of two-dimensional, I would say, a set of numbers which has 2 dimensions, which means we add one additional dimension here to this beta, and then this will automatically take care of the fact that we should also have a beta naught, right? So now coming back to the y equal to x beta, this is the matrix representation for the predictions mapped to the inputs. All right. So now let's see how we can find what is the least square fit, because this is never ever going to happen. What I wrote here, this is never ever going to happen. This will be approximately 10. What is exactly going to happen is, let me move it here. Then this plus some error 1 can become 10. This plus some error 2 can become 20. This plus some error 3 can become 30. This plus some error 4 can become 40. This can happen. But if these error terms are not there, this line alone will never match individually with every single data points. It's not going to happen. So what can we actually do if we want to find the best possible line? What is the best possible line, by the way? The best possible line is something that reduces the error to a minimum. And in this particular case, what is the error? We can denote error by something called as residual sum of squares. Residual sum of squares is not at all a scary term. It's fairly straightforward. Error is nothing but let's say this is your data. If you say that this is the straight line that maps with this data, you are having a huge residual sum of square, because what is the residual sum of square? This squared plus this squared plus this squared plus this squared plus this squared, right? So it is basically sigma of yi minus y actual I, this is y predicted I squared. That is residual sum of squares. And this will be minimum if the line is passing somewhat like this. If the line is on an average closest to all these points, then this sum of residual squares will be the minimum. So our goal is to reduce the or minimize the sum of residual squares. So now how do we represent it in terms of matrices? It's like this. So residual sum of squares, this RSS, equal to the absolute value of y minus x beta the whole square. So why have we written y minus x beta? Because we were trying to say that this is predicted y, that's why there is a cap here. But in reality, the actual y values only approximate with x beta. So y minus x beta will always be it will never be exactly equal to 0 unless all the points happen to be exactly on one straight line. But otherwise, this will not be exactly equal to 0. This will be something different from 0. So if we take the square of this, then that is called, if you take the square of this particular matrix, y minus x beta, then it's the residual sum of squares. And we can expand it in this following. So this is y minus x beta transpose. Imagine, understand that this is a matrix. This is not a scalar. This is also a matrix. So let's say matrix A matrix minus matrix B the whole square is basically A minus B transpose times A minus B, right? So that is what we have done here, y minus x beta transpose times y minus x beta. Now there is one thing that I want you to note here, just a small mathematical detail. So let's expand this term by term to understand this matrix multiplication. So what is y minus x beta transpose times y? So that will be y transpose times y. Then what is A, B transpose? It's equal to B transpose, A transpose. So this is a basic identity within matrix transposes. So we can apply that here. So y transpose y, that is from this y transpose times y, then minus x beta transpose times y minus y times x beta plus x beta transpose times x beta. So this much is straightforward, normal expansion. Now just look at this. What is this, each of these individual terms or this entire term as such? This is a scalar. Like, although these are individually matrices, this is a scalar. So every single individual terms that are being added or subtracted here is a scalar. So y transpose y is a scalar. As you know, it will be, let's say y is a matrix of dimension n by 1. Sorry about the handwriting. Y transpose will be 1 by n. Then when you multiply y transpose and y, it will be multiplication of two matrices of 1 by n and n by 1. And this will result in something of 1 by 1. So all of these are just scalar numbers. So which means now if you look at these two terms, so this is term 1, term 2, 3 and 4. Let's look at term 2 and 3 for now. Ignore term 1 and 4. So term 2 is now x beta transpose times x transpose y, right? This can also be written as this is equal to its own transpose, because beta transpose x transpose y transpose. Why is that the case? Because a transpose of this 1 by 1 matrix is the same as itself. So adding a transpose is not going to change it. Now what is this? This will be y transpose times beta transpose x transpose the whole transpose. So beta transpose x transpose the whole transpose, and this will be y transpose x beta. So term 2 is y transpose x beta. I think I am missing a y transpose term here. Yeah, so there is a transpose missing here. So now overall, term 2 will be y transpose x beta. Term 3 is also y transpose x beta. There is a negative sign to both of them. So that is why it became minus 2 y transpose x beta. Plus the last term is beta transpose x beta. Because when you expand this bracket term, it will become the beta and x will flip. Beta transpose x beta. Right? So let me maybe move this a bit aside. Otherwise, it is becoming a bit cluttered. All right, never mind all these messed up things. But here, this finally becomes the expansion. Now, what is our goal? Our goal, singular goal in linear regression is to minimize the sum of residual squares. And how do we find the minimum? It's an extreme, which means you just find dou RSS by dou beta. So that is here, dou by dou beta of this term. So you can already see that this has no beta term. So if we are taking the dou by dou beta of this term, so let's call it as term 1 plus term 2 plus term 3 plus term 4. Term 1 is not having any beta term, so you can ignore it. Then it is just actually term 2 and 3 we combine into one single term, right? So let's write it like that. So it's just term 1, 2, 3. That's it. 4 we can ignore. Then term 2 has beta in it. Term 3 also has beta in it. So what is dou by dou beta of this? Dou by dou beta of this is minus 2 x transpose y. So this also needs some explanation. So when we are taking derivatives of using matrices, there has to be proper accounting of dimensionality. So a simple rule that you can memorize, or you can just remember, is that dou by dou b of, let's say, A transpose B. Imagine A and B are matrices. Then dou by dou b of A transpose B equal to actually A. It's not A transpose. So if you can kind of take me for granted on this one, then you can do the dou by dou beta of this term is anyway 0. Dou by dou beta of minus 2y transpose x beta, right? So this is essentially this whole term we call as the A, which means dou by dou beta of this entire expression equal to transpose of whatever I have put in this circle here. So it will be minus 2y transpose x whole transpose. 2 I am putting outside, equal to minus 2 x transpose y. So that is what you see here, minus 2 x transpose y. Similarly, how about this? Dou by dou beta of beta transpose x transpose x beta. So this we can write in the following way. So this equal to, so here there is beta in this term. So let's first split here in this term as well as in this term, right? So this will be equal to beta transpose x transpose x. So that is the A term, the whole transpose. So it's like this. So for example, d by dx of f of x g of x equal to f prime g plus g prime f, right? Something like that. And then plus we can do dou by dou beta of this term, beat plus dou by dou beta of beta transpose x times beta. So this equal to, if we expand this x transpose, the last x will become x transpose. It will come to the first part times transpose of this whole thing, which will be x transpose, which is x, times beta transpose, it is beta, plus here we can write this in another form, dou by dou beta of x transpose x beta, the whole transpose, times beta. So what I did is I took the transpose of this. So I first took the transpose of this and then wrote it as the transpose. So you just imagine the transpose of this. So if you take the transpose of x transpose x beta, then beta will go to the left side. It will become beta transpose, right? And x transpose x, the transpose of that will become, it will be to the right side. It will become x transpose x itself. And now we can write this as x transpose x beta plus you can say dou by dou beta of x transpose x beta, the whole transpose beta, which is equal to x transpose x beta plus, now this is again of the form dou by dou beta of a times beta, and this will be a transpose, which is the transpose of x transpose x. Transpose of x transpose x is x transpose x itself. So this will become x transpose x beta, and this will be 2 times x transpose x beta. And that is what I have written here. Where is that? Here, 2 times x transpose x beta. So that is how you expand. Now what we should understand is, what are we trying to do here? We are trying to minimize the residual sum of squares such that dou RSS by dou beta equal to 0, which means if this is equal to 0, then 2 times x transpose x beta equal to 2 times x transpose y. And then we can bring everything to one side such that, beta is on one side and rest of the terms are on the other side. So how do we do that? We simply multiply both sides of the equation. So first of all, delete 2 and 2, and then multiply both sides of the equation by inverse of this term. Because inverse of this, if it's here, then both of them will cancel to become the identity matrix, right? So we have x transpose x beta equal to x transpose y. Now we multiply both sides. Let me make some space here. X transpose x whole inverse is multiplied over here. Then x transpose x whole inverse is multiplied here as well. And you can see that these two inverse matrices will cancel to become identity matrix. So identity matrix beta equal to x transpose x the whole inverse x transpose y, which means beta equal to, beta itself is a matrix, beta equal to x transpose x inverse x transpose y. And what is this beta? This beta is nothing but the P1, P2 thing which we were writing here, right? Where is that? This guy. So we said we added one more dimension to the x, as the first column will be series of ones, array of ones. And then the beta is the coefficient matrix, which is the matrix which represents the beta naught, beta 1, beta 2, beta 3, etc. in the linear regression. And so this is how we solve for beta, by minimizing the residual sum of squares. All good. I feel confident enough that now when we implement this in code, at least you will understand what's going on. Because this equation, if I had directly dumped in front of you in the code, you would not understand what exactly is happening. But at least now, hopefully, even if you haven't understood the derivation fully, you please watch it again. It's not complex at all. I'm sorry if my handwriting has made it a little bit confusing, but just watch it once again. It's not complex. But basically, you will now understand why we are using a certain equation in the code implementation when we are implementing linear regression from scratch. When we are implementing linear regression using existing packages, this is not needed. But when we are implementing from scratch, you will understand it much better. So now let's implement the code in Julia. So I have already written the snippets of code in Julia, and I will first walk you through the code manually, and then we can start the coding. So the first snippet is implementing the basic mean squared error calculation, the manual from scratch version of this. So let me open the pen. Okay. So we are using two packages, using linear algebra, this one, and statistics. Statistics we have been using throughout the lectures, but what we are going to do now is create a data set and try to compute the coefficients which we described above. So first, the independent variable x, it's actually just 1, 2, 3, 4. Now you might be wondering, what is this one? These series of ones are nothing but the appended array. So we discussed earlier that we do append a series of ones so that we can represent in matrix form 1, 2, 3, 4. Okay, we don't have 5, so this is not there. So this is basically what this is. And y is the predictions or the output corresponding to the input x. So it's 2, 2.5, 3.7, 4. Okay. Now here we are directly computing beta. So earlier we saw that beta, if we do dou RSS by dou beta equal to 0, then we got beta equal to x transpose x, the whole inverse, times x transpose y, right? That's what we calculated up here, x transpose x whole inverse times x transpose y. So that is what is written here. And this particular operator, this it's called reverse slash or something, right? This operator basically helps us perform this calculation without explicitly calculating the inverse. So the end result will be same as what this equation is saying, but here we are not explicitly calculating the inverse. This is much more efficient. And then we can print the coefficients. Now, what are the predictions? Predictions, we know y cap equal to x beta, right? So that is what we are doing here. Y pred equal to x times beta. This is, again, remember, matrix multiplication. These are not scalars. And then we try to kind of print the mean squared error, because we want, our whole idea was minimizing mean squared error. So we calculate mean of y minus y predicted dot raised to 2. Dot raised to 2 means you're doing element wise square, because y has multiple, like 1, 2, 3, 4. Y has 4 values. So every single value every single value of prediction we are subtracting from the actual value of y, and then squaring it, and then summing it up, and then taking the mean of that. So mean squared error. And I made a mistake, I think, in the previous. Now that I remember, I want to fix it. So here I said square root, right? Actually, if there is square root, it's like RMSE, not mean squared error. So just check this. That was a mistake. In mean squared error, you won't have the square root. So just take notice of that. Now let's come back to the code. And then we just print the mean squared error, right? So now what we can do is, let's open Julia. So go to terminal. If you are on Windows, go to the, what is it called? The Windows command window. So terminal, and let me zoom in. So here, obviously, you should have Jupyter Notebook installed. Throughout this course, we are implementing in the Julia in Jupyter Notebook. So I have Jupyter Notebook and I have Jupyter Lab. I also have Julia for Jupyter installed. This was covered in detail in the first lecture. If you don't remember, or if you don't have this, just go back to the first lecture and do this. It won't take you more than 5 minutes. Now this should open the server here, the local host. All right. So we have the Jupyter Notebook open, and then click View and open Jupyter Lab. View, open Jupyter Lab. And then we will open a fresh Jupyter Notebook. File new. not Julia. I want Julia notebook. So Julia 1.1.1, 1.11.1. And to save the time, let's just copy this code. We have already explained this in detail. So let's run this. Yeah, statistics is needed for the mean. I am not entirely certain if we require the linear algebra package or not. I guess it's needed to do this operation. So first, let me do it without this linear algebra package. Hopefully, it should throw some error, mostly in this line. Okay, there is no error. All right, then no issues. Statistics is definitely needed, because if statistics is not needed, mean should throw an error. Let's see. Oh, because I have already, I guess, loaded this before. I think this is when you are running for the first time, most likely this will be needed, because if I remember correctly, to run this operator, you might need this package. I'm not fully correct. I'm not fully sure. Then statistics for mean. In any case, let's just rename this notebook and as linear algebra. So the coefficients beta are 1.24 and 0.72. Can we guess what is this which one is intercept and which one is slope? We can see that when we are plotting this, the 1 is corresponding to 2, 2 is corresponding to 2.5, 3 corresponds to 3.7, 4 corresponds to 4. So perhaps the slope is 0.72, the second one, and the intercept is 1.24, the y-intercept. And let's see the predictions, right? So the predictions are like this. For x value equal to 1, instead of actual value being 2, the predicted value is 1.97. When x is 2, the predicted, instead of 2.5, it's 2.69, 2.7, close to. If x is 3, instead of 3.7, the predicted value is 3.41. This is where the most deviation is. Then when x is 4, prediction should be 4, but it's 4.13. Not bad. And mean squared error is actually quite low. It's 0.0345. It's fairly good. One more thing is the visualization. So I wanted to sort of kind of plot the predictions as well as the line as well as the points. So let us do that also. So I have made a scatter plot using the plots.jl. So it's a scatter plot of 4 points, and the 4 points are all the x values, which are not the predictions, the data points, and the red line is the least square fit line. And the fit line is passing through the points really well, but you can see that the second and third points are deviating, and the intercept is it's not 0, but it's 1.24, and the slope is 0.72. So this is how you can visualize how well you are trying to fit the line with a new prediction, fit the line with the existing data and make a new prediction. We can also find now the value corresponding to an x data point which was not there. So for example, a data point 2.5 is not part of the original training data. Original training data had just 4 points. But now if someone asks, okay, if the x value is 2.5, what should be the prediction? The prediction will be somewhere here. It will be 3.1, something like that. We can input this into the equation of the line, and we can get back the exact value. But this is how you implement linear regression fit from scratch, and it all boils down to this one single equation. Of course, one more thing was this appending of the extra ones over here. So if you remember this and this, you can implement linear regression in pretty much any programming language, actually. In some programming languages, I'm not sure if the provision for calculating calculating beta without calculating inverse is explicitly present or not. But if you can implement this equation as a matrix calculation, and if you can have the input x with ones appended in the first column, I think you can calculate even without the help of any linear regression package. You can calculate these predictions. Okay, now let's also, as the last thing today, in this lecture, let's also use libraries. So today we'll be using a library called MLJ, and what it's going to do, not MLJ, in fact, this guy, linear regression package, because previously what I had written here was the one for manual, like the from scratch implementation of linear regression, but I want to show you it using GLM. GLM, I think it's called General Linear Models. Julia, GLM, general or generalized, something like that. Yeah, generalized linear model. So this GitHub repository has good number of stars, almost 600. So just check it out. I mean, you can directly use it here. So what I'm going to do is like, let me show you first the code. So in the first code block, we are importing the libraries, data frames for storing the X and Y DF, then GLM, and then here there is a random, and random is nothing but this for this random seed. So this is for reproducibility when we are running the code and when we are creating random input values. So here you see rand is used for, if we don't have this, the kind of values that are created in the rand function will be very different. But when we use the same kind of seed, then we will get similar kind of X values even while running the code multiple times. So, but this is actually not needed. I am fine with this also not being here. So data frames, GLM and using random. So let's copy this and let's put it in a new block. Okay. Now we are creating a random data set. So X values are random.seed for reason it's not a unary operator. I guess, yeah. So now I just want to print the values. Okay, so just look at this is Y values, I guess. So print ln, I don't want 100, I just want 10 just for demonstration. Print ln of X and print ln of Y. So just check these values, and if we were to, let's say, run this once again, these are different values. But now let's try this with seed. These are the set of values. See, when we are inputting the seed, the numbers that are generated are exactly, I mean, they are random, but this time it's exactly the same, 9.06. So if seed is, let's say now, I don't know what seed can we put, like if any random number can be put as the seed or not. Let's see, 51. See, if the seed is the same, the generated numbers will be the same. They will be random, but they'll be very reproducibly random. But I mean, we don't need this at all. So I don't care about the seed. Let's just delete that line of code. And let's just keep n equal to 10, just 10 numbers. Now we copy this part of the code where we convert this whole thing into a data frame, the X and Y values, the randomly generated numbers into a data frame. And then we call the linear model, and this is the syntax. So here the input to the linear model is the data frame, and we are fitting a linear model which maps the input X to the Y. And let's also display the different parameters, R squared and coefficients. So coefficients are beta. Okay, I think they already printed the model summary. Okay, it's because that was the last line of code. So model summary is the following. The intercept value is 3.28. It should be I guess the Y intercept, and lower 95%, upper 95%, Y approximately 1 plus X. And I just want to plot it to see how this whole thing looks like. First 5 predictions. x, y predicted. So you can see that the y value and predicted y value, the actual y value and predicted y value are fairly close. And last thing, the visualization. Right. This is a fairly good fit, but I just want to give you a brief idea about what are the different terms here, which is mentioned in the model summary. So the main things to notice are the y-intercept, the slope 2.4144, and the confidence standard error, which is I think it's like a mean value of epsilons. And then lower 95 and upper 95 is something like, if it's the 95% confidence interval. So if this current set of 10 data points, which has a certain distribution, if it is replaced with another set from a similar kind of distribution, how confident is what is the slope and intercept of the model for the 95% confidence interval? So for the slope, the confidence interval is between 1.85 and 2.42. So what that is saying essentially is that this model is sure that 95% of the cases, the slope will lie between 1.85 and 2.42 if a new set of 10 data points are generated from a very similar kind of distribution. Because this data set were random, it was between an upper value and lower value created at random. So from a similar type of random number generator, if you were to generate another set of 10 values, this model is 95% confidence that the slope will lie somewhere between 1.855 and 2.42 in 95% of the cases, and intercept will lie somewhere between 1.53 and 5.03 in 95% of the cases. Let's plot with some larger number of values instead of 10. Let's say 100, 1000. It will look very good. The graph will be very interesting to see. I think this predictions part will probably take some time, I guess, because it did not take time. Actually, it was quite fast. Y predicted not found in the data frame. Okay, so yeah, so these are 1000 random numbers, and this is the straight line, and you can see that the 1000 random numbers are really nicely fitting to the line because the way we have created it using this formula, something like beta naught plus beta 1 times a random value x. So that's what we did. So I mean, it makes sense that it is fitting through a straight line. I am very interested to see the model summary in this particular case. Okay, so in this case, the coefficient is 3.40, and it is very close to this guy. It's very close to 3.5, the intercept value that we use here. When x is equal to 0, y is 3.5. And the slope that we used here is roughly close to 2.2. And here also it's saying the same thing. So slope is 2.2. And the confidence interval has now become much more better, because now the model is saying like it's fairly confident that the y-intercept will be between 3.28 and 3.52 in 95% of the cases if another set of 1000 points were to be created with a similar kind of random distribution. And it's also confident that the intercept will be between 2.18 and 2.22 in 95% of the cases. So this is very good. And if it is 100, I guess the confidence interval will reduce a little bit more. This is 100, and confidence interval reduce, meaning confidence will reduce, the interval itself will expand, and you can see that that's what's happening. So I think this brings us to an end of this lecture. Irrespective of whether you are trying to learn Julia or not, it doesn't matter that the programming language in this particular case, I think we comprehensively covered linear regression. I think in this much detail, I actually did not expect the lecture to be this long, but it has ended up becoming quite a long lecture. But if you have managed to finish this in one sitting, I really congratulate you. But feel free to pause it. Feel free to go back and revise some portions which were not so straightforward. And I once again want to take a moment to appreciate you for following through with this course and reaching till this point, because I want you to stay motivated. I want you to finish the lectures sequentially without without pausing, or without pausing meaning without breaking away from the course at some point, which usually happens. So if you have reached till this point of the course, you have already come a long way compared to most of the students. So really, congrats to you for that. We will see again in the next lecture. And now in the remaining part of this module of machine learning, we'll be covering logistic regression, k-means clustering. I think there is principal component analysis and a couple more concepts. So this entire module will be purely focused on machine learning models, simple machine learning models. After that, we'll be entering into deep learning. So thank you so much for listening. We'll meet again in the next lecture. Take care until then. Bye.